everyone. How are you all? I hope you all are doing well. First of all, it's a very warm welcome to you all in our channel Euclid Mathematics. In my today's video, we are gonna learn subgroups, groups, and how to find it. Okay, for odd order prime elements using first milestone in our group theory, which is a Lagrange's theorem. Already I uploaded more videos on my channel from group theory subject and other subject too. All higher mathematics subjects I uploaded in my channel. So you can refer my all videos from my channel, okay? For better understanding of the concepts, I uploaded more examples and their solutions. If you have any doubt, please let me know in comment section. So I will upload more videos as per your difficulty and doubt. So then let me know if you have any doubts or difficulty. So let's dive directly to our today's topic and we see how one can find subgroups and group of a subgroup, okay, by using Lagrange's theorem with the help of a prime element. Okay, I selected here in my today's example prime elements. Okay, so you can see it here in my example. First I selected order of G is a P and Q. Okay, these are the general elements. I consider it the P multiplied by Q, and P and Q we have to consider it is prime. Okay, because non-prime element is quite easy to find their values. Okay, so P and Q you can select any prime number. Okay, and one condition it is here P strictly less Q. Okay, the value for P which is smaller than Q, then the number of subgroup of P and G non-abelian. Okay, we want the number of subgroup of P and when G is a non-abelian. Okay, and PQ we have to consider for short time it is a prime. Okay, so let's get started our solution of example. Okay, so we have order of group is a P multiplied by Q. Okay, and P smaller than Q. Then we have to find out first of all element of order. Subgroup of order it's easier to find, but first of all we need to know the element of order, then we will move further for subgroup of order. Okay, for element of order we know that by using Lagrange's theorem we can guess it here which number of order possible to our group. Okay, so by Lagrange's theorem we know that group order divided by subgroup of order. Okay, so possible subgroup we will get it here. Okay, order of G is here P multiplied by Q. Okay, which is given in example, and Lagrange's theorem it says that order of subgroup can divide order of group. Okay, so what is the possible element which divides order of group as a PQ? So one is possible element. P is also possible element because P divides PQ. P is also prime, and Q divides PQ. Q also prime. Okay, and PQ divide PQ it is also possible. Okay, that means these are the four elements which are the possible subgroup of our group. Okay, now let's figure it out which one of the subgroup which is possible. Okay, so we know that if G non-abelian, so which is given in our example, G is a non-abelian. If G non-abelian, then we say that G is non-cyclic. Okay, if group is non-abelian, then it is a non-cyclic. Or you can check it here, if the group of order and its element of order not equal, then we say that it is a non-cyclic. Okay, and it is non-abelian. So if group is a non-abelian, that means there exists an element whose order which not possible PQ. Okay, if order of a group is a PQ and there exists an element if it is order PQ, then by cyclic, okay, the definition of a cyclic group, we can say that group order and their element order, their elements order are same, then our group is a cyclic. And if it is cyclic, then it is abelian. Okay, but we have given G is non-abelian. Okay, that means the subgroup of order PQ it is not possible. Why not possible? Because our group is non-cyclic. And why it is non-cyclic? Because the element our group is given non-abelian. Okay, non-abelian implies non-cyclic, and our group order PQ, and there does not exist element of order PQ. So PQ possibility for PQ it get cancelled here. Okay, now let's go further. If G is non-abelian, then G has element of order PQ. Okay, but if then when it is possible, the element of order G are left over here P and Q. Okay, 1 PQ, and we always know that the element of order 1 only possible when our group has an identity element. Okay, so you can see that the element of order 1 in a G is only 1. Okay, because identity is the only element. Okay, whose order possible 1. Okay, least positive power we are taking here for finding their element of order. Okay, so which is a to the power n is equal to 0, and n is the least positive integer. So similar here, identity is the element whose order 1, because a to the power n least positive 1 it is only 1. Okay, okay, so identity element is here whose order is 1. Okay, now let's go for the next order of a Q. Okay, number of element of order Q. So you can take it P or Q, nothing matter because both are prime and having prime values. Okay, so number of element of order q in a G. Okay, so we know that the for finding number of element of any element in a G, we use a phi of q. Okay, and if q is a prime, then phi of q is a q minus 1. How q minus 1? If I select q as a 7. Okay, if I select q as a 7, then phi of q. Okay, if q as a 7, I select here, so I will explain here q I consider q as a 7. Okay, so I want the phi of q. Euler phi function is there. Okay, that means phi of 7. So how to find phi of 7 by Euler phi function? So write that 7 here. Try to find out their smallest divisor here. So we know that it is a prime. It cannot get divided by any number. Okay, so it divisible by 1 only, 7 only. 7 ones are 7. So we can see that I got the value for p is here. P is here as a 7. Okay, and phi of p is equal to 1 minus 1 upon p1. Okay, this is p1. Okay, 1 minus 1 upon 7. Okay, you can see that 6 minus 6 1 7 1 is 7 minus 1. Okay, and multiplied by n it is here. Okay, and n it is a 7. 7 1 is 7 minus 1, which is a 6 by 7, and it get cancelled with 7, it remains 6. Okay, so you can see that phi of q I consider q. Okay, phi of q I consider is a 7. So phi of q means 7 minus 1. Similarly, like a phi of q means q minus 1. Okay, how it is q minus 1? Because it is a prime number, and when we take it as Euler phi function for prime number, it get one element lesser than our total number of element. Okay, so I got the element of order 1, which is 1, and element of order q in a G is a q minus 1. Okay, so then total number of element of order 1 and q, how much total 1 and q is a q minus 1 plus 1. Okay, that means addition of these two elements of order. Okay, so total number of order 1 and q is a, which is equal to 1 plus q minus 1. Okay, this plus this, so 1 plus q minus 1 plus 1 minus 1 get cancelled, it remain only q. Okay, so total number of order 1 and q is a q only. Okay, so now you can see it here, we have possibility for element of order, okay, 1 pq, and pq get cancelled here. Okay, it is not possible because of non-abelian. So I got the element of order which is a q, and element of order which is a 1. Okay, which is totally p minus 1, which is a q 1 plus q minus 1, which is a q. Okay, now it's a left over here, though we want the element of order p. Okay, so how to find element of order p? Now let's see it here. I got the 1 and q, which is a q. Then the number of remaining element in a G. Okay, order of G we know that pq. So if we try to take away that q from our group of order, okay, so our group of order is a pq. So try to take away that q from our group of order. So now left over the elements are there, which is an element of order p. Okay, then the order of remaining element in a G is a p. Okay, so left over element p, and then number of element of order p in a G. Okay, so order of G, total order of G, it is here q, sorry, pq. Okay, order of G is given in example, which is a pq, and the element of order 1 and q is a q. So if I'm trying to take away that q from our G, so left over element is of the order p. Okay, so order of G pq minus q. Okay, so this is the element where our group contain. Okay, so p contain, so pq minus q, which is an element of order p. Okay, so take a q out from this bracket, so p minus 1 into q. Okay, so I got the three element here, three element which is having order 1, which is identity element, other element q, which is a q minus 1. Okay, so whose order is a q minus 1, and left over it is here the element of order p, which is a p minus 1 into q. Okay, so this is the way to find out the subgroup, okay, of our group. But we have to very careful about the element which has given property. Okay, the group which has given property, so it is here non-abelian. Okay, that's why we are able to omit that pq as a possible subgroup. Okay, so we omit that one, then it left over here. Okay, so instead of pq you can replace any value. Okay, you can replace any value for that pq and try to find out whether our group which is a having subgroup of different order or not. Okay, so it's quite easier to find out with substituting the value for pq. Okay, so here number of a subgroup of order p in a G. Okay, so we know that for finding subgroup of order any order of our group, we know that number of subgroup of order D in G, which is a number of element of order D in G. Okay, number of element of order that certain element in a G divided by pi of that certain element. Okay, so we want the number of subgroup of order p in G. Okay, so how many elements are there? So number of element of order p in a G is a p minus 1 into q. Okay, divided by phi of p. Okay, number of element of order D in G divided by phi of D. Okay, so phi of p it is here, and phi of p is a p minus 1. Okay, so p minus 1 get cancelled with the pi of p. Okay, which is a p minus 1, and left over here it is a q. Okay, so number of subgroup of order p in G is a q. Okay, you can see that how easy it is. So first element, identity element whose order is 1. Okay, q element whose element of order is a here q minus 1, and the element of order p is a p minus 1 into q. Okay, so the number of subgroup of order p, okay, the number of subgroup which we want in our example, which is a p minus 1 into q divided by pi, okay, which is a q here. Okay, let's solve some examples by using this property. Okay, so here example first, you can see order of g is equal to 6. I consider it is the 6 because I can write it that group as a multiple of a 2 prime element. Okay, so order of g is equal to p into q. Okay, and you can see p smaller than q, p smaller than q, it is our property, and g is a non-abelian. Okay, if group g is a non-abelian, then we can see that p subgroup of order q, okay, subgroup of order p is q. Okay, and p is smaller and q is bigger. Okay, and that means here 3 subgroup of order 2. Okay, p subgroup of order, subgroup of order p is a q. Okay, then a subgroup of order 3 is a 2. Okay, so this one is easier. Using above property, you can easily say that without finding the subgroup. Subgroup of order 3 is a 2. Okay, similarly go for the if group of order is 55. Okay, which can be written as 5 into 11. 5 11s are 55 and 5 smaller than 11. And g non-abelian. If g is non-abelian, then we can apply the above property. Subgroup of order p in a g is a q. Okay, that means p and q, p is a 5 here and q is 11 here. Okay, subgroup of order 5, then we can write that one g has 11 subgroup of order 5, that means 11 p subgroup of order q. Okay, g has a order p in a g is a q. Okay, subgroup of order p in g is q, that means g has 11 subgroup of order 5. So we have to apply that property. It is here for the other examples. Okay, I hope so you all have understood. These are quite easy examples that you easily we can answer by using above property. So if you have any doubt, let me know in comment section for my today's lecture. Thank you everyone. Thank you for my today's lecture.